In 1826, a man pointed a pewter plate out of his upstairs window and then waited, not for minutes, but for 8 full hours. And when he finally pulled it back inside, he held in his hands the only object on Earth that had ever captured a moment of real time. That man was Nietzsche Fournier Peace, and the plate in his hands would become the oldest surviving photograph in human history. But the real story didn't start with Nietzsche PC. It started with silver, a soft, unremarkable metal that had been sitting in the earth for billions of years, quietly hiding one of the strangest properties in all of chemistry. Silver doesn't like light, specifically certain compounds of silver, silver chloride, silver bromide, react when photons hit them, breaking apart at the molecular level and leaving behind tiny deposits of dark metallic silver. Alchemists noticed this centuries before anyone understood why it happened. They'd leave silver salts on a windowsill and come back to find them turned black, as if the sunlight itself had stained them. For most of history, this was treated as a nuisance, a weird quirk of the metal, nothing more. Then, in 1727, a German physicist named Johann Heinrich Scholz decided to actually test it. He mixed chalk with silver nitrate, poured it into a bottle, and held different sides of the bottle up to the sun. The side facing the light turned dark almost immediately. The side in shadow stayed white. Scholz went further. He cut letters out of paper, wrapped them around the bottle as stencils, and exposed the whole thing to sunlight. When he peeled the stencils off, the letters were there, burned into the surface in dark silver. He had, essentially, just made the first photograph, except he hadn't, because 10 minutes later it was gone. The moment he brought the bottle inside and tilted it, the dark silver particles tumbled and mixed with the white ones, and the image vanished. You could capture light, but you couldn't stop it from destroying what it had just made. That problem, how to fix an image, how to make it permanent, would consume the next 100 years of scientific effort. It also meant that Scholz's discovery sat largely unused, a curiosity filed away in the footnotes of natural philosophy, until a French landowner with too much time and a genius for tinkering decided to pick it back up. Nietzsche wasn't a chemist in the academic sense. He was a gentleman inventor, the kind who fills a workshop with failed experiments and keeps going anyway. By the 1820s, he'd already helped invent an early internal combustion engine and a working bicycle predecessor, but his real obsession was making images fix themselves permanently. His solution wasn't silver at first, it was bitumen. Bitumen of Judea, to be precise, a naturally occurring asphalt that hardens when exposed to light and stays soft where it's shielded. He coated a pewter plate with a thin layer of the stuff, slid it into a primitive lens box aimed at the courtyard outside his upper floor study window, and left it there for roughly 8 hours. What came back was blurry, barely legible. You can see a rooftop, a hint of a courtyard, the ghost of a pigeon house. But it was real, it was permanent, and it did not fade. The world had its first photograph, and almost nobody noticed. Napes needed a partner with access to better optics, so he wrote to a Paris theatre set painter named Louis Daguerre, who had built a reputation for creating breathtakingly realistic painted illusions using lenses and mirrors. The two men signed a partnership agreement in 1829. Nietzsche died 4 years later, never knowing what Daguerre would discover next. Daguerre had been experimenting with silver-coated copper plates, sensitizing them with iodine vapor to create silver iodide on the surface. Another light, reactive silver compound, far more sensitive than bitumen. The plates needed less than 30 minutes of exposure, which was an enormous improvement, but they still weren't good enough. Then, in 1835, Daguerre made the accident that changed everything. He left an exposed plate inside a wooden storage cabinet overnight, and when he came back the next morning, the image had developed far more clearly than anything he'd achieved in the camera. Something inside that cabinet had acted as a chemical developer, dramatically darkening the silver particles that had absorbed light, making the image visible in minutes rather than hours. After systematically removing items from the cabinet one by one over several weeks, Daguerre found the source a small dish of mercury that had been left on a shelf, slowly releasing vapor at room temperature. Mercury vapor was interacting with the exposed silver iodide, creating a mercury-silver amalgam that produced far brighter highlights and sharper detail than anything before it. By 1839, when the French government announced the daguerreotype process to the world, giving it away completely free as a gift to humanity, people lined up around the block in Paris to buy the equipment. Studios opened overnight. Portrait painters started panicking, and the world began the strange new habit of freezing time. There was one catch nobody talked about in the brochures. A daguerreotype portrait required the subject to sit perfectly, absolutely still for anywhere from 3 to 15 minutes, depending on the light. Studios installed iron head clamps, metal braces bolted to the chair that locked the sitter's skull in place to prevent blur. The stiff, unsmiling faces in those early daguerreotypes aren't stoicism. They're the physical result of someone fighting not to twitch for a quarter of an hour with their head locked in a metal vise. That problem, speed, would define the next century of photographic development. George Eastman cracked the mass-market version of it in 1888 when he introduced the Kodak camera, a small box preloaded with a roll of flexible film coated in a gelatin emulsion packed with millions of microscopic silver halide crystals. Each crystal was a tiny light trap. When a photon hit one, it kicked loose a few electrons, which rearranged silver atoms into an invisible latent image baked into the crystal itself. Chemical development later amplified that signal into a visible photograph. For the first time, you didn't need a darkroom, a chemistry set, or 15 minutes of sitting still. You needed a button and a second. Eastman's slogan was, "You press the button, we do the rest." He meant it literally. When you'd used all 100 exposures on the roll, you mailed the entire camera back to the factory, and they processed the film and mailed you prints. The camera came back loaded and ready. Film ran the world for nearly a century, and silver ran film. Roughly 140 million troy ounces of it every year at film photography's peak, most of it going straight into photographic emulsions. Then, in 1969, 2 engineers at Bell Laboratories in New Jersey built a device so conceptually strange that their own colleagues thought it was a toy. Willard Boyle and George Smith spent about an hour sketching the basic architecture of the charge-coupled device, the CCD, on a whiteboard, working from the same semiconductor physics that had produced the transistor in that same building 22 years earlier. The idea was simple and revolutionary. Instead of using silver crystals to catch photons, you used silicon, a semiconductor that releases a tiny electrical charge when struck by light. Arrange millions of these silicon light wells in a grid, read out the charge levels row by row, convert those numbers into digital values, and you have an image made entirely of data. No chemistry, no silver, no weighting. Early CCD sensors were crude. The first video camera to use one produced images of roughly 100 by 100 pixels, which looked less like a photograph and more like a ransom note assembled from blurry squares. But the physics was sound, and silicon followed Moore's law while silver did not. The sensors got smaller and denser every 2 years, packing more and more light, catching elements, pixels, into the same physical space. By the early 2000s, consumer digital cameras were shipping with sensors containing 3 million, then 5 million, then 8 million individual pixel wells, each one smaller than a red blood cell. Your phone right now almost certainly contains a sensor smaller than your pinky nail that packs in 48 million individual light, catching elements, each one capable of measuring the intensity of red, green, and blue light independently, thousands of times per second. The shutter speed on a modern smartphone camera can hit 1/10,000th of a second. A piece needed 8 hours. That's not an improvement in degree, it's a transformation in kind. What changed wasn't just speed or convenience, it was the economics of the moment itself. When a photograph cost money, when you had 24, 36 shots on a roll and development fees waiting at the other end, you chose carefully, you framed, you waited for the right light, you asked people to hold still, or at least hold a smile. Every shot was a small investment. Now every shot costs nothing, and so we take everything the half-eaten plate, the slightly better version of a photo we took 3 seconds ago, the moment that didn't need capturing but got captured anyway. Humanity now produces more photographs every 2 minutes than existed in all of the 1800s combined. Somewhere in that number is something worth sitting with. 300 years ago, a man noticed that silver goes dark in sunlight and called it a nuisance. A century later, another man pointed a plate at a window and waited all morning for a smear of light to become something permanent. And now, in the time it took to read this sentence, someone on the other side of the planet pressed a button and froze a moment that would have vanished forever, all because silver doesn't like the sun.